So the pH is defined as being the negative log of the concentration of the H3O plus ions. So you work out that concentration, then you put that number in the calculator, do the appropriate things with the buttons, and you work out the pH. Yeah? So, for our 0.1 mole per litre HCl solution, the pH is the negative log of the concentration of the hydronium ions, which is the negative log of 0.1, and that should come out as being 1 on your calculator. Right? If it doesn't, then you need more bonding time with your calculator. And then I've got a couple of other ones here, just to practice using your calculator with, unless you want to do them in your head. Any of you do that in your head because you know about logs? No? Cool. Excellent. Doesn't matter. Second one, pH is going to be 5. Are we getting this on the calculators? Yeah? Okay, there's 2 more. Oh. If you're someone who could do them in your head, you probably can't do that one, so that's to make you push the buttons. You can work out that that one should be 1.64. pHs are always 2 decimal places, unless there's very good reasons for them to be 3, but normally only 2 decimal places. That's kind of a feature of logs. So don't go quoting the pH to all the numbers on your calculator, because then it will actually be wrong. Right? You won't just be silly, you'll be wrong. So 2 decimal places. And then we have this one. If you were to go downstairs to the chemical store and get a bottle of Conc HCl, then it would say on it that its concentration is 16 moles per litre, which is pretty syrupy and nasty. What would be the pH of that one? Hopefully you can work out that it's... So if the HCl solution is said to be 16 moles per litre, that means the concentration of H3O plus ions is 16 moles per litre, and that means that the pH is negative 1.2, and that's okay. It's one of the things you see repeatedly in school books, is that they say that the pH scale is from 0 to 14. This is bollocks. You can have negative 1.2 very happily. If it was sulfuric acid, you can have, it's a smaller number, that's negative 1.5 or something. And these superacid things, which I mentioned, you can have pHs of negative 5, negative 6, crazy numbers like this, yeah? So it isn't really just 0 to 14, it's a lot bigger than that. Okay. Now, very important, note that even though the concentration of the H3O plus ions might be very low, we would still call the acid a strong acid because its reaction with the water goes to completion. Right? So it's this difference between strong and weak acids versus concentrated and dilute acids. Yeah? You can have a very dilute solution of a strong acid, because a strong acid is defined as being strong because of the way it reacts with the water, not because of how much H3O plus there is in the solution. Does this make sense? So strong acids and weak acids are a different thing to concentrated acids and dilute acids. Okay. Everyone's happy so far? If you're a strong base, then there's a similar sort of way that you can quantify how basic the solution is using something called the pOH. And it's kind of the same deal because the little p is still the same thing. The little p stands for the negative log. And so the pOH is just the negative log of the concentration of hydroxide ions. And so if you had a 0.02 moles per litre solution of sodium hydroxide, then that means that you've got, because all the sodium hydroxide completely dissociates in the water to give sodium ions and hydroxide ions, then the concentration of hydroxide ions will be the same as that starting concentration that we give you, just like it was for HCl. So the concentration of hydroxide is 0.02 moles per litre, and so the POH is just the negative log of 0.02, and that's 1.7. And so in both cases what you can say is that the bigger the number gets, the bigger the pH gets, or the bigger the POH gets, the lower the concentration of the hydronium ions or the hydroxide ions in your solution. Okay? And then finally, you need to be able to do this as well. So if we give you a concentration of H3O plus ions, we need you to be able to work out the pH. If we give you the pH, you need to be able to convert that back to a concentration of H3O plus ions. And so this is the way that you would write that down on paper. You say that the concentration of H3O plus equals 10 to the power of the negative pH. Right? And so if you look at your calculators, what you should find is that the button that's got LOG written on it, above that, it should have 10 to the x, 10 to the power of x written above it. Yeah? Because in each case, you've got the button, and then shift the button, which gets you that a function that's printed above the button is the undoing of the function that the button does. Right? So if you hit the log button, it does the log. If you go shift log, it does 10 to the power of, which is the undo of the log function. Yeah? So I think that in the tute there's going to be practice for this, but this is something you want to be really, really comfortable with, because it's not only, we're not only going to use these sorts of log functions for this, but for a bunch of other stuff later on as well. Okay, so we're good with strong acids and strong bases. These are the relatively straightforward ones. And what that means is that typically these are the ones we're less likely to ask you about in first semester, right? We're going to teach you it again, but we're much less likely to examine you on it. We're going to examine you on the harder stuff, right? Which is what we're coming to, which still isn't that bad, but nonetheless, okay? Right. So the strong acids and the strong bases are the straightforward ones because their reactions go to completion. At the end of the day, most acid-base calculations and questions we ask you will involve working out the pH. And to work out the pH, you need to know what the concentration of H3O plus ions is in the solution. And so for strong acids and strong bases, that's easy because the reactions will go to completion. The ones which are more complicated are the weak acids and the weak bases. Because a weak acid is one where when you put it in water, it will react with the water to give hydronium ions and a conjugate base molecule, but it will only do that a bit. And then you will reach an equilibrium where you no longer get any overall reaction. And so an example would be this one, CH3COOH. This is acetic acid, or ethanoic acid, or foodic acid. I saw it once written as on the back of a bottle. This is the one that's in vinegar and in lemons and stuff. And this is probably the most likely weak acid you're going to see, because we chemists aren't very interesting. So CH3COOH will react with the water molecule. It's this H here, which is the one that comes off when this acts like an acid and donates a proton. This is the one that gets donated to the water. So what we're left with is CH3COO minus and hydronium ions, H3O plus. And this reaction does not go to completion. You form an equilibrium, so we write this with an equilibrium arrow in the middle. And what that means is that it's much more complicated to work out what the concentration of H3O plus is, compared to one like this where we know that all of this reacts to make H3O plus, so working out that concentration is easy. Here, there's more work to do. But weak acids are important because, like we said earlier, there's only really about 4 or 5 or 6 strong acids out there, but there's gajillions of weak acids. And in Chem 191, the chemical basis for biology and human health, with about one exception, all the acids that you come across in your body are going to be weak acids. And their chemistries are fundamentally important to understanding how your body works, and so weak acids are something you're going to see a lot of. Not only in chemistry, but if you go on in biochemistry or all sorts of other things, you're going to come across these a lot. Right? Because it's an equilibrium, we can write an equilibrium constant expression. And we do this using all the rules that we learnt for writing equilibrium and constant expressions last week. For the equilibrium that you get with a weak acid reacting with water to make hydronium ions, we write what's called the acid dissociation constant. And that word's a little bit old-fashioned because it kind of goes back to when we used to just write CH3COOH goes to H plus and CH3COO minus and not include the water. These days we tend to include the water in the equation because it really is in the equation. But the name still holds, so the acid dissociation constant, but the symbol for it is Ka. A big K for equilibrium constant, but now A for acid. Just like we had KSP last week, now it's Ka, A for acid. Yeah? And so for that equation that we just had for the acetic acid, here it is here again, the Ka would look like this. Remember, it's concentrations of products raised to their stoichiometric powers divided by concentrations of reactants raised to their stoichiometric powers. You don't put in solids and you don't put in liquid water. And so what you're left with is this, that the Ka will be the concentration of the acetate ions, the CH3COO minus, the acetate ions at equilibrium, times the concentration of the hydronium ions at equilibrium, divided by the concentration of the unreacted acetic acid molecules at equilibrium. Okay, so just the same sort of thing as we saw last week. And please remember to put the E's in. Have any of you had any problems with the guys across the way about the E's? Them telling you don't need them? No? Good. Put the E's in. Because as we're going to see shortly, putting the E's in here, again, means that when we come to do the calculation to work out the pH, you can very clearly indicate in your working how the process is going if you put the E's in. Okay. The value for the Ka, remember Ks are equilibrium constants, they're just numbers which give you an idea about how much of the reaction happens before you reach equilibrium. The Ka for CH3COOH is 1.74 times 10 to the negative 5. 0.000174. This is a little number. And so what that tells you is that not very much of the ethanoic acid, or look, I'm being good, the ethanoic or acetic acid, it's the same thing, yeah, actually donates its protons to the water. Most of it stays as CH3COOH molecules in the solution. And so this is why we call it a weak acid, because it's not very good at giving away its protons. And again, what we do is someone's decided once that 1.74 times 10 to the negative 5 is an awkward number. And so to make it an easier number to deal with, we do something called the pKa. Right? So the negative log of the Ka value. And so we will either, in a question, give you the value of the Ka for a weak acid, or we'll give you the value of the pKa. And sometimes you need the pKa, and so you'll have to turn the Ka into the pKa, and sometimes you'll need the other way around. So you need to be comfortable about changing it one way and back the other way as well. And so for ethanoic acid, you could quote the pKa as being the negative log of 1.74 times 10 to the negative 5, and that turns out to be 4.76. Right? And so the same thing applies if you have 2 or 3 different weak acids. You can compare them using their pKa's. The bigger the pKa value is for the acid, then the poorer the acid is at giving away its protons. Right? And you can work through that by thinking about how the Ka expression works. But sometimes we'll do that. We'll give you 2 or 3 different weak acids and say which of these is the strongest, and which of these is the best acid, not the strongest, because then that just gets confusing. The best acid, and so it will be the one that has the smallest pKa value. Right? And I said earlier that about this business about not having to remember which acids are strong acids. Anytime we give you a weak acid, then we will either ask you to work out the Ka for it, or even more likely, we will give you the Ka or the pKa. So if we give you some random acid you've never seen in your life before, but we give you a pKa value for it, then that immediately tells you it's a weak acid. Because strong acids don't form equilibria, so they don't have a pKa value. Right? So if we give you an acid and it's got a pKa value along with it, then that means it's a weak acid. If we give you an acid and there is no pKa value, then it must be strong. Yeah? What's next? Right. A weak base is one that does not completely give hydroxide ions when you put it in water and it reacts with the water. Sorry, when you put it in water, it doesn't completely turn into hydroxide ions. Right? So sodium hydroxide, you put it in water, it completely dissociates, and all the sodium hydroxide turns into sodium ions and hydroxide ions. A weak base is one that doesn't do that completely. And there'll be some ionic compounds which would act as weak bases like this. Something like, so if you had a sparingly soluble hydroxide compound, maybe like calcium hydroxide, then that might count as a weak base. But what you find much more commonly is rather than ionic hydroxides, like sodium hydroxide or something, weak bases tend to be molecules that react with water to make hydroxide. Right? And so the most common example of that would be ammonia, NH3. If you take ammonia and you put it in water, then the ammonia molecules can react with the water molecules. The ammonia is a base. It's a weak base, but when it does act as a base, it acts by taking a proton off the water molecule. So the water molecule in this reaction is acting like an acid, right? It donates a proton to the nitrogen, and so you end up NH3 turning into NH4 plus, because we've added an H plus to this, so it goes to NH4 plus, and what we're left with on our water molecule is OH minus, right? The water's lost an H plus, so what's left behind is a hydroxide ion. So when ammonia gets placed in water, you make hydroxide ions, and so you make a basic solution. But because this is an equilibrium, you can't just work out the amount of ammonia that you add, and then because it's 1-to-1 mole ratio, immediately know the concentration of hydroxide that's there. You have to work it out, right? So it's a weak base because it's an equilibrium situation. And we can write a Kb for that, B for base, which now is going to have hydroxide in it rather than hydronium ions like we saw before with the acids. So the Kb for ammonia will be the concentration of ammonium ions, NH4+, at equilibrium, times the concentration of hydroxide ions at equilibrium, divided by the concentration of the ammonia molecules at equilibrium. And so we could look up the value of that Kb in a book if we wanted. We could also work out a pKb from that Kb if we wanted to, and so on, just like we've seen for Kas. It's the same ideas, except talking about a different chemical equation. A base, in this case, rather than an acid doing its thing. I think that's probably time for it. Yes, sir.
So you mentioned that that bases dissolve in water. Here it reacts. Is that
Yeah.
only apply to strong bases?
Strong bases are the ones that dissolve in water. Weak bases are the ones that react with water. I think that's probably for pretty much everything you're going to see in first year, that's going to be true. So, yeah.